Welcome to OLED Black Crush. My name is Timothy Lattis, and this is the Neo Kino Graphics channel. Today we'll be talking about this TFT Central article. Does OLED have a black crush problem? Understanding and testing OLED shadow detail. Initially, their graph looks a little confusing. Gamma 2.2 should be a continuous curve. Oh, I see later they are plotting the RGB. It's sRGB that has the linear segment around 0. When I added larger dots to the graph, it makes a lot more sense if the dots are aligned to the values at the bottom. So this is wonderful. TechPress is posting some measurements. I measured this kind of step function around black on the first OLED TVs long ago. I was looking into what are the limits of OLEDs for doing HDR, specifically HDR in a dark room. So you'd run with really low average picture level, and then you would get into this problem where your shadow detail just crops out into this black crush zone. Now it's 2026, and TFT Central is publishing some amazing graphs. And in general, it's TFT Central and others who are actually deep diving into these important topics. However, I do disagree with one statement that TFT Central makes. TFT Central says, in the case of OLEDs, we're looking for the display manufacturers to have made adjustments and perceptual optimizations near black in one way or another to improve detail. And I think this is actually wrong. I would rather have an accurate Gamma 2.2 curve. As a developer, we can always introduce user-controlled knobs to adapt near black behavior to the local viewing condition. But the only way we can accurately do that is if the transfer function is known. And if the display manufacturers are putting in some random transfer function, it makes it very hard to work around. So the actual first visible black level is a little more complicated. It will vary across the screen based on content. Note, it will also vary across the screen based on ambient and specular reflection on the screen itself, i.e. the room viewing conditions. So when we think about black crush, we should be really thinking about the two aspects separated. The first aspect is what could actually be visible based on the viewing conditions. And the second aspect is what the display can actually reproduce at some frames per second. And we should not couple these two things. Now, in the early days of Black Crush versus today, what's the difference? Perhaps it was the same issues at different magnitudes. Early on, it seemed as vendors couldn't reproduce near black with any accuracy, and then you add on top of that the pixel drift across time of the OLED pixels, and the result would be visible patterns, almost like burn-in. And so the marketing alternative defaults to clamping that region to 0. Today, however, we got a lot more range in FPS on the displays, and it does seem to be more display FPS dependent. Showing one of the more extreme cases below from the TFT Central article. TFT Central says that the OEMs only calibrate at 1 Hz, and that does seem to correlate with what they're showing in the graph. At 280 Hz, it looks like RGB 1, 2, 3, 4, 5, 6, and 7 all output the same value. Question is, why? If we go back to older plasma TVs, they used a very visible spatial temporal pulse width modulation. So as FPS doubles, you'd have half the PWM subframes, and thus the ability to display near black effectively cuts by a stop each time. But this is not what's going on with the OLEDs. You notice that Blurbusters himself mentioned in 2023 that there's some kind of faint once per refresh cycle partial brightness dip on most OLEDs. And note, this effect likely plays more of a role at higher FPS. Going back to the TFT Central article, they say this seemingly doesn't impact QD-OLEDs. And they show the brightness dip sync to refresh rate on WOLEDs. Yet if we go to TFT Central's reviews of QD-OLED panels, you'll notice that they also have the same refresh dip. If we look at TFT Central's BFI scopes, you can see the actual pixel transitions. In this shot, we have a QD-OLED on the left running at 120 Hz versus a WOLED on the right at 270 Hz. You'll notice at higher Hz, the transition inaccuracies dominate the signal more. So for instance, on the left-hand side, you'll notice that there's almost a linear segment between the point at which the transition ramps up and the point at which the transition ramps down. That's at 120 Hz. But on the WOLED on the right, by 270 Hz, you notice there really isn't much of a linear step in there. It mostly transitions up and then transitions down. Both of these should be doing a square wave if they were completely accurate. Now, it's very hard to tell if the QD-OLED is more square than the WOLED because of the change of frame rate, but it doesn't look like it's significantly that much different. So we'll have to find another reason to why we're having these problems that don't affect QD-OLED as much as they affect the WOLEDs. So TFT Central's VIR Flickr article gives some more hints. So at low pixel values, like RGB value of 5 in their example, and at high FPS, You notice that this refresh dip limits the pixel transition. There's not enough time to get it stable enough, and this is what's actually causing the black crush, for the most part. You'll also note that VRR is a lost cause, because one doesn't know how long the frame will last, and thus there's no way to know what value to compensate this for. For example, we could calibrate the monitor at every refresh interval, and as the refresh interval increases and the display time goes down, we would just pick a different compensation value based on that knowledge. But since you don't know how long the frame will last, there's no way to pick the right compensation. And thus it's better to just hit VSync and calibrate your LUTs for that specific frame rate. As I was writing this, TFT Central came out with another article. This one is even better than the prior, exploring the gray banding issue affecting some Tandem WOLED panels. They do confirm the low current accuracy issues that we were seeing before. In fact, they have an official response from LG and others. One thing TFT Central didn't get into was the actual reason QD-OLEDs are better than WOLEDs. And I think the reason is pretty self-evident. Say you want to drive a linear RGB ratio of 30, 34, and 36 in a very, very dark pixel. For a WOLED, that might translate to driving a linear RGB-W ratio of 0, 4, 6, and 90. This would represent the minimum linear ratio of RGB to W. You might increase the amount of RGB and decrease the amount of W. The net result is the RGB channels in RGBW likely get driven a lot less, and this implies more time in the microcurrent poor accuracy zone, which we're seeing problems with. Back when I had an LG WOLED panel, I didn't like the chroma artifacts I would see in the darks. Luckily, we do have a lot of in-shader workarounds for all these kind of problems. All these come in the form of energy redistribution. So for instance, we can use shader energy redistribution, BFI, to shift more energy out of the black crush zones and put them towards the first frame in a series of frames. For in-display black crush, we can discard the lower end steps of 8-bit output and then use spatial temporal blue noise to manually dither there. We can have the end steps be under user adjustability, and note games need to dither anyway because 8-bit has visible banding. But this must be energy conserving dithering, otherwise the effect won't work. If you dither after you've gone to gamma 2.2, you're doing it wrong. For the room reflection aspects of black crush, we can have a user knob which sets the in-game target average picture level. This works by adjusting in-game exposure and not brightness, and it does this before tone mapping. In a bright room, one increases the APL, and in a dark room, one can decrease the APL. These provide very simple solutions to the problems that we're seeing on WOLED panels with the best of our ability, meaning these aren't perfect, but in an imperfect world, we'll take the best we can get. And I'm going to close there. Until next time.